Good afternoon, my dear students. Welcome to the GATE online classes, session 6. Today we are going to discuss about some other bandpass transmission techniques. Differential phase shift keying, differentially encoded phase shift keying, DEPSK, quaternary phase shift keying, QPSK, 8 phase shift keying, 8PSK, and also we are going to discuss about some objective type questions and gate oriented problems. In the last session, we have discussed about the binary bandpass data transmission techniques, BASK, BFSK and BPSK, in order to convert the digital data into analog data to transmit over free space. In BASK, the amplitude of the carrier is varied in accordance with instantaneous value of the modulating signal. So here the modulating signal means symbol 1 and symbol 0, digital data. One is transmitted by means of transmitting a carrier of a fixed amplitude and fixed frequency, and 0 is transmitted by means of turning off the carrier. Whereas in BFSK, the frequency of the carrier is varied in accordance with instantaneous value of modulating signal. So here symbol 1 and symbol 2 are represented by means of two different frequencies, FC1 and FC2, which are defined as mark frequency and space frequency. And in BPSK, the phase of the carrier is varied in accordance with instantaneous value of the modulating signal, where symbol 1 is represented by means of transmission of carrier with 0 phase, and 1 is transmitted by means of another phase. So these are the three important techniques, and all these three techniques can be implemented by using coherent modulation schemes, where the locally generated carrier used at the receiver has to be perfectly in synchronism with the carrier that was used at the transmitting side with respect to both frequency and phase. And this basically requires a complex carrier recovery circuit and bit synchronizing circuit at the receiving side, so which is costly. BASK and BFSK can be implemented non-coherently, but BPSK cannot be implemented non-coherently. So since here phase is the constraint which is going to transmit symbol 1 and symbol 0, therefore the phase must be in synchronism with the one which was transmitted at the transmitting side, and hence differential phase shift keying is used, which is known as DPSK. So it is a non-coherent form of PSK. DPSK is an alternative form of digital modulation, where the binary input information is contained in the difference between two successive signaling elements rather than the absolute phase. Okay, so the binary input information is in the difference between the successive signal elements rather than absolute phase. Therefore, DPSK is the non-coherent form of PSK, and it avoids the need to provide the synchronous carrier required at the demodulator for detecting a BPSK signal by suitably modifying the PSK generation scheme. And it avoids the need for complicated circuitry, which is used to generate a local carrier at the receiver. So DPSK is a non-coherent form of PSK. Now let us see the DPSK modulator, how to generate the DPSK modulator. So the DPSK modulator comprises with an exclusive OR gate and a delay element and a balanced modulator. So this balanced modulator acts as a phase reversing switch, so which is a PSK modulator. So DPSK transmitter contains a differential encoder followed by PSK modulator. So this combination of exclusive OR gate and delay element is a differential encoder followed by PSK modulator. So to eliminate the need for phase synchronization of the receiver with PSK, we may incorporate this differential encoding. In differential encoding, we encode the digital information contents of a binary data in terms of signal transitions. So symbol 0 is used to represent no transition in a given binary sequence with respect to the previous encoded information. and symbol 1 is used to represent transition. So here the data stream to be transmitted, which is represented by D of T. So this is applied to the input of the exclusive OR logic gate. So the output of exclusive OR gate is D of T delayed by the time TB is applied as another input to the exclusive OR gate. So which is represented as B of T minus TB. Okay, so D of T is applied as one input and the output B of T, which is delayed by 1 unit, is given as the second input to the exclusive OR gate B of T minus TB. So this B of T is D of T exclusive OR B of T minus TB. Here the upper level of the waveform corresponds to logic 1, which is indicated by +1 volt, and lower level of the waveform corresponds to logic 0, which is indicated by -1 volt. So the upper and lower logic levels are indicated by +1 and -1 for D of T, B of T and B of T minus TB. So here this figure shows that the logic levels and their corresponding voltage levels. Okay. Now let us consider a binary bit string. Let us consider a binary bit string 001001100111. So we want to transmit this information. Okay. So first this 0 has to be transmitted at the given as input to this exclusive OR gate, and arbitrarily assume the first interval B of 0. So let us assume that B of 0 is equals to 0. Okay, B of 0 is equals to 0. So we have to arbitrarily assume the first interval B of 0. So B of 0 must be either 0 or 1. Since it may be 0 or 1, no other possibilities, only two possibilities. Therefore our result is valid quite generally. Okay, so if first bit is 0, data bit is 0 and arbitrary bit is 0, we have assumed that B of 0 is equals to 0. Therefore the exclusive OR output is now T of T, B of T minus TB, which is equals to 0. So 0 exclusive OR 0, which is equals to 0. So now B of T is equals to 0. Okay, exclusive OR operation. Now this becomes B of T minus TB for the next bit. So this is the next bit 0. For this bit, when we transmitted it through the exclusive OR gate, this becomes the second input to the exclusive OR gate. And the 0 exclusive OR 0 is equals to 0, which is B of T. Now this B of T is second input to the next bit 1. Therefore 1 exclusive OR 0 is equals to 1 now. Okay. And now this becomes the second input to the next bit 0. Next bit 0. Therefore 0 exclusive OR 1 is equals to 1. So in this way we will generate B of T minus TB. B of T minus TB. Okay, so once we have generated this B of T minus TB, B of T is from this point. So this is B of T now. So for the first bit, this is B of T. For the second bit, this is B of T. For the third bit, this is B of T, binary input. Therefore, B of T is 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1. So this becomes the B of T. Okay, that means it is the output of this exclusive OR gate. That is difference output. This is the difference of these two bits. So the B of T is the output of differential encoder. Now this differential output is given as input to the balanced modulator, which is a phase shift key modulator, PSK modulator. So B of t is one of the inputs to this balanced modulator, and other input to this balanced modulator is the carrier signal. Okay. So here in this case the waveforms are drawn on the assumption that the interval 1 B of 0 is equals to 0. Okay. So this is actually the invariant feature by which we have characterized the system would continue to apply. Since B of 0 must be either 0 or 1, our result is valid because only two possibilities. So suppose if we start with B of 0 is equals to 1, then the levels B of 1 and B of 0 would have been inverted. Okay. Now this B of t, the output of this encoder, differential encoder, is applied to a balanced modulator as one input and carrier A cos omega ct as another input. Therefore, this balanced modulator acts as a phase reversing switch. Okay. Therefore, the output of the balanced modulator is B of t root over 2ps cos omega naught t or A cos omega naught t. Since we have already discussed, A can be written as root over 2ps. Okay, so this is the dpsk output. So dpsk is plus A cos omega ct when logic 1, B of t is at logic level 1. And when B of t is at logic 0, then V dpsk is equals to minus 1 volt. Minus 1 volt. Okay. So this is B of t, and this was encoded by the encoded phase is this 0 is encoded as 180 degrees out of phase. So this is simply a PSK modulator. So 0 is represented by transmission of a carrier of 180 degrees phase shift, and again 0 is 180 degrees phase shift, carrier with 180 degrees phase shift. One is transmitted with a carrier with no phase shift. One is transmitted with a carrier with no phase shift. Similarly, here for 1 it is 0, for 0 180, for 1 it is 0, and for 1 it is 0, for 1 it is 0, for 0 it is 180, for 1 it is 0, for 0 it is 180, and for 1 1 it is 0 0. So this is the encoded phase for B of t. Now if you see the transition phase shift, B of t minus tb, B of t. So the transition phase shift is 0 phase when there was no transition in B of t and B of t minus tb. Okay. So since if you see B of t minus tb and B of t, so here there was no transition of state. Therefore, the output phase is 0. The transition phase shift is 0. And here also 0 to 0 transition. Therefore, output phase shift is, transition phase shift is 0. And for 0 to 1 transition, there was a 180 degrees phase shift. 1 to 1 means there is no transition. Same level, 1 to 1. Therefore, 0. So, here the transition phase shift is 0 for 1 to 1 transition or 0 to 0 transition. And 180 degrees phase shift when 0 to 1 transition or 1 to 0 transition. So this is the transition phase shift. So when B of t, if you see B of t is equals to 0 when the transition phase shift is 0. See, B of t is equals to 0 when transition phase shift is 0. And for D of t is equals to 0, the phase shift is 0. For D of t is equals to 1, there was a 180 degrees phase shift. And for 0, there was a 0 transition phase shift. For 0, it was 0. And for 1, 180 degrees. And for 0, 0, 0, 0. And for 1, 1, 1, 180 degrees phase shift was there. Okay, so when D of t is equals to 0, the phase of the carrier does not change at the beginning of the bit interval. While when D of t is equals to 1, there is a phase change of magnitude 180 degrees. Okay, so this is the concept involved in the differential phase shift keying. Differential phase shift keying. So instead of transmitting as absolute phase, we are going to represent the DPSK output by means of the difference between two successive bit intervals. Okay, the phase of two successive bit intervals. And if you see this particular figure, so D of t, so this diagram represents D of t. So D of t is 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0. And B of t minus tb, if you see the B of t minus tb, 0, 0, 0, 1, 1, 1, so 0, 0, 0, 1, 1, 1, and 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, okay, and 0, 1. And B of t is, this is B of t. So B of t is represented as 0, 0, 1, 1, 1, so 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1. So if you carefully observe this one, from this figure, D of t is equals to 0, D of t is equals to 0, when B of t and B of t minus tb are equal. T. When B of t minus tb equal, in that particular case, D of t is equals to 0. Okay. And when B of t is equals to B of t minus tb bar, when these two are complements, that means when B of t minus tb is 0 and B of t is 1, in that particular case, D of t is equals to 1. D of t is equals to 1. See, B of t is equals to B of t minus tb when D of t is equals to 0. And B of t is equals to B of t minus tb when D of t is equals to 1. Okay, so this is the concept involved in the differential phase shift keying. Differential phase shift keying. Now let us see the DPSK demodulator. DPSK demodulator. So the DPSK demodulator comprises with a multiplier and a delay element. Okay, so here the DPSK input may be, the receiver input may be B of t root 2 ps cos omega ct plus theta to represent B of t as 1 or minus root over 2 ps cos omega ct plus theta to represent B of t as 0. So let us assume that one of the two inputs are given as inputs to this multiplier as one input. Okay, so here the received signal and the received signal delayed by the bit time tb are applied to the multiplier. Okay, so this is received signal and received signal delayed by one time unit is applied to the multiplier. So here the multiplier does the multiplication operation. That means B of t root 2 ps cos omega ct plus theta multiplied by B of t minus tb root over 2 ps cos omega c t minus tb plus theta. Since here delay is there, so here the output of delay unit is the same as the received signal, except there was a time delay of tb units. Okay, so therefore the output of this multiplier is the product of these two. So which is given by B of t minus tb a square cos omega ct plus theta into cos omega c into t minus tb plus theta. Okay, so this is in the form of cos a, cos b, so that we can represent this one as cos a plus b plus cos a minus b. Okay, so that the multiplier output can be written as B of t minus tb a square cos omega c tb plus cos 2 omega c t minus tb by 2 plus 2 theta cos a plus b plus cos a minus b. Okay, and now this is applied to an input to an integrator circuit. So this is applied to an integrator circuit, so which will suppress the double frequency term. So this is the double frequency term, and this can be suppressed by the integrating circuit. Therefore, the multiplier output integrator output becomes B of t multiplied by B of t minus Tb cos omega CTB. Okay. So in this case, omega CTB has to be selected such that it is equals to 2n pi. So omega CTB is selected such that it is equals to 2n pi, with n as an integer. Since in this particular case cos omega CTB is equals to plus 1. Cos omega CTB is equals to plus 1. If you select omega CTB is equals to 2n pi. So and obviously the signal output will be as large as possible. And further with this selection, the bit duration encompasses an integral number of clock cycles, and the integral of double frequency term is exactly 0. Therefore, the transmitted data bit d of t can readily be determined from the product b of t and b of t minus tb. So this becomes 1. So this is completely depends on the product of b of t and b of t minus tb, since a square is a constant. Okay. So if d of t is equals to 0, that is the data input, d of t is equals to 0, then there was no phase change. When d of t is equals to 0, so we have seen that there was no phase change, and hence b of t is equals to b of t minus tb. When d of t is equals to 0, then b of t is equals to b of t minus tb. So we've seen that d of t is equals to 0, b of t and b of t minus tb are same. Okay, so if d of t is equals to 0, there was no phase change, and b of t is equals to b of t minus tb. Okay, and both being plus 1 volt or both being minus 1 volt. Both being plus 1 volt or both being minus 1 volt. So in this case, b of t multiplied by b of t minus tb becomes 1. The product of b of t and b of t minus tb is equals to 1. Okay. However, if b of t is equals to 1, then there was a phase change, and either b of t is equals to 1 with b of t minus tb is equals to minus 1, or b of t is equals to minus 1 with b of t minus tb is equals to plus 1, when d of t is equals to 1. Since there was a phase change, there was a transition either from 0 to 1 or from 1 to 0. So therefore, if b of t is equals to 1, b of t minus tb is equals to 0, and their logic values are plus 1 volt, minus 1 volt. Okay, so therefore, the product b of t multiplied by b of t minus tb is equals to minus 1. It is minus 1. Okay, so in this way, so we can demodulate the output. We can demodulate the DPSK output. Okay. Now coming to the disadvantages of DPSK. Noise in 1-bit interval may cause errors to 2-bit determinations. So in DPSK, a single bit determination is based on the basis of a signal received in two successive bit intervals. Hence, noise in 1-bit interval may cause errors to 2-bit determinations. Therefore, the error rate in DPSK is greater than in PSK. And there is a tendency for bit errors to occur in pairs, so which is not invitable, but single errors are still possible. Because here we do not make a hard decision in each bit interval about the phase of the received signal. Hence, single errors can also occur. Okay, so these are the disadvantages with DPSK system. Now let us see another bandpass modulation technique, differentially encoded phase shift keying. So in DPSK demodulator, it requires a device which operates at the carrier frequency. So since we have transmitted the received signal and its delayed version of the signal as inputs to the multiplier. That means a carrier frequency which is operates at the carrier frequency and provides a delay of TB. But DEPSK eliminates the need for such an hardware. So in DEPSK, the synchronous demodulation recovers the signal B of t first, and the decoding of B of t to generate D of t is done at the baseband. Okay, then D of t is done at the baseband. So first B of t is decoded, and then D of t is recovered from the knowledge of B of t. Hence, it doesn't require the carrier frequency, the component which is operated at the carrier frequency. And coming to the DEPSK modulator, the modulator of the DEPSK system is identical to the transmitter of the DPSK. Okay, and DEPSK modulator. So this figure shows the DEPSK modulator. So it contains an exclusive OR gate and a delay element. So here first the signal B of t is recovered exactly the same manner for BPSK system. Okay, and then the recovered signal is then applied to one of the inputs to this exclusive OR gate, and to the other input B of t minus TB is applied. That means 1 unit delay is applied at the another input of this exclusive OR gate, which is equals to B of t minus TB. And the gate output will be one of the two levels depending on whether B of t is equals to B of t minus TB or B of t is equals to B of t minus TB bar. Okay, so since D of t is exclusive OR of B of t and B of t minus TB. Okay, so therefore, if B of t is equals to B of t minus TB, B of t is equals to B of t minus TB. So we have seen that B of t did not change level 1, and therefore the transmitted bit is D of t is equals to 0. Okay, so we have seen that B of t, when B of t is equals to B of t minus TB, when both these are same, when B of t minus TB is same, then D of t is equals to 0. The transition phase shift is 0. So 0 phase shift indicates transition the bit of 0. Logic 0. Okay. So B of t is equals to B of t minus TB, then D of t is equals to 0. And if B of t is equals to B of t minus TB bar, B of t is equals to B of t minus TB bar, then the output is 1. Then the data is equals to 1. Okay. So this is the DEPSK demodulator. B of t is equals to B of t minus TB, then D of t is equals to 0. B of t is equals to B of t minus TB bar, then D of t is equals to 1. Now coming to the disadvantages. So in DPSK there is a tendency for bit errors to occur in pairs, but single bit errors are also possible in DPSK system, differential phase shift keying. But in DEPSK, errors always occur in pairs. So the reason is, in DPSK, we do not make a hard decision in each bit interval about the phase of the received signal. So we simply allow the received signal in one interval to compare itself with the signal in an adjoining interval, and a single error occurs. Therefore, single error occurs. So we will compare the current signal and the adjoining interval, the signal in an adjoining interval. Therefore, single errors are also possible. But in DEPSK, a hard decision is made in each interval about the value of B of t. So if we make a mistake, then the errors must result from a comparison with the preceding and succeeding. So let us see one example for this one. So let us suppose B of k is given by this bit stream 011, 011, 00, and B of k minus 1 is 0, 1, 1, 0, 1, 1, 0, 0. Now, D of k is exclusive OR operation between these two. D of k exclusive OR D of k minus 1. So, therefore, 1 exclusive OR 1, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0. So, this is when no error. Okay, so this is the output for the error-free signal when B of k minus 1 are with no errors, when B of k with no errors. Suppose let us assume that there was an error in the fourth location. There was an error in the fourth location. Then if there was error in the fourth location, so instead of 0, here it is 1. Here it is 1. Therefore, that reflects an error in the B of k minus 1. That reflects an error in the B k minus 1. Therefore, when we do the exclusive OR operation, the output is 1, 0, 0, 0, 1, 0. So, if you compare this result with this D of k, there was 2 errors. There were 2 errors here. Okay. So, we have assumed that B dash of k has single error. Then B dash of k minus 1 must also have a single error. And therefore, D dash k has 2 errors. Therefore, in DEPSK, the errors always occurs in pairs. So, this is the disadvantage with the DEPSK system. Okay. Now, let us see another important bandpass transmission technique, that is quadrature phase shift keying, QPSK. Basically, for binary FSK, PSK, the number of possible conditions are 2. Number of possible conditions are 2, either 0 or 1. Therefore, these are M-array systems with M is equals to 2. So, these are also known as M-array systems with M is equals to 2. Binary. So, this M is replaced with binary systems with M is equals to 2 and N is equals to 1. That means each symbol is transmitted by means of 1 bit. 1 bit. Okay. PSK system with 4 output phases is an M-array system with M is equals to 4, which is referred to as QPSK. So, QPSK is an M-array encoding scheme where N is equals to 2. That means the number of bits transmitted for each symbol is 2 and M is equals to 4. M is equals to 4. Hence the name quaternary phase shift keying or quadrature phase shift keying. Quaternary means 4. So, a QPSK modulator is a binary signal with base 2 which produces 4 different input combinations. 4 different input combinations 0, 0, 0, 1, 1, 0, 1, 1, because we are going to transmit 2 bits as a group. So, in binary PSK, only 1 bit is transmitted, whereas in QPSK, 2 bits as a group are transmitted. Okay, therefore, 4 possible combinations are there 0, 0, 0, 1, 1, 0 and 1, 1. Therefore, with QPSK, the binary input data are combined into group of 2 bits which are known as debits, which are called as debits. So, in the modulator, each debit code generates one of the 4 possible output phases with a phase difference of 90 degrees. Therefore, for each 2-bit debit clocked into the modulator, a single output change occurs. For each 2-bit debit in the modulator, a single output change occurs. Therefore, the rate of change at the output, which is known as baud rate, is 1/2 of the input bit rate. The baud rate is equals to 1/2 of the input bit rate, since we are transmitting 2 bits in a symbol period. Okay. So, this is the advantage of QPSK. So, the quadrature phase shift keying can be interpreted as 2 independent BPSK systems. So based on its modulation process, it comprises with I channel and Q channel, and each channel is interpreted as a independent BPSK system. And therefore, the performance of the QPSK is the same as the BPSK, but twice the bandwidth efficiency. Twice the bandwidth efficiency, since we are transmitting 2 bits. So 2 bits are transmitted in a single modulation symbol. Now let us see the modulator, QPSK modulator. So this figure shows the QPSK modulator. And it consists of a bit splitter, a I and Q bits, and balanced modulators, reference carrier oscillator, and linear summer, and then the output. So here the inputs to this the QPSK modulator is a 2-bit group. A 2-bit group, that means 00, 01, 10, 11. And the 2 bits are clocked into the bit splitter. The 2 bits are clocked into the bit splitter. After both bits have been serially inputted, they are simultaneously parallelly outputted into these I and Q channels. Okay, so one bit is directed to the I channel and other is directed to the Q channel. Okay, so one bit is towards I and another bit is towards Q. Okay, so the I bit modulator, so this is the I bit modulator, and this is the Q, that is quadrature phase section. So this I bit modulates the carrier that is in phase with the reference oscillator. That is in phase with the reference oscillator. And this Q bit modulates the carrier that is 90 degrees out of phase with the reference oscillator. 90 degrees out of phase with reference oscillator. So once these 2 bits has been split into I and Q channels, the operation is same as that of the BPSK modulator. So once we have transmitted this 2 bits into I channel and Q channel, then it simply, each of these blocks simply acts as 2 parallel BPSK modulators. Okay, so 2 parallel BPSK modulators which are combined in parallel. So here logic 1 is represented by +1 volt and logic 0 is represented by -1 volt. Since so we are transmitting a bit 0 or 1, and here also we will transmit a bit 0 or 1. Therefore the bit 1 is represented by means of +1 volt and bit 0 is represented by means of -1 volt. So 2 phases are possible at the output of in-channel balanced modulator. I channel is nothing but in-channel balanced modulator. Okay. So what are those? +1 into sine omega ct, -1 into sine omega ct. Okay, and 2 phases are possible at the output of Q channel balanced modulator. Q channel balanced modulator. +1 into cos omega ct and minus cos omega ct. Therefore, here at the output of I channel balanced modulator, we will be having 2 phases with plus sine omega ct, minus sine omega ct. And for Q channel balanced modulator also, we will be having 2 phases, plus cos omega ct and minus cos omega ct. Now, when the linear summer combines these 2 quadrature signals, there are 4 possible resultant phases. There will be 4 possible resultant phases. One is plus sine omega ct plus cos omega ct, minus sine omega ct plus cos omega ct, plus sine omega ct minus cos omega ct, minus sine omega ct minus cos omega ct. So these are the 4 different phases that will be appeared at the output of linear summer. Okay, so that is treated as the QPSK output. The output of the linear summer is the QPSK output. So let us take an example for, suppose if you want to transmit a debit 0, 0. We want to transmit debit 0, 0. So 0, 0 means, so the it is first sent to the bit splitter, where the bit splitter parallelly transmits these 2 bits into I channel and Q channel bits. Therefore, for this I channel, the bit is 0 is transmitted, and for this Q channel, bit 0 is transmitted. Okay, and now the 2 inputs to the I channel balanced modulator are -1 sin omega Ct. So at the balanced modulator, what are the 2 inputs? Since we have transmitted 0, so 0 is represented as -1 volt. Therefore, the one input to the balanced modulator is -1 volt, and another input is the reference carrier oscillator generated carrier sin omega Ct. Therefore, the input to this balanced modulator is -1 and sin omega Ct. Okay, and at the Q channel balanced modulator, the 2 inputs are -1 and cos omega Ct. -1 and cos omega Ct. Okay. Therefore, the output of the I channel balanced modulator is -1 multiplied by sin omega Ct, because these 2 are the inputs to the balanced modulator, and the output of the Q channel balanced modulator is -1 into cos omega Ct, since these 2 are the inputs to balanced modulator, Q balanced modulator. And now these 2 are applied to the linear summer, and the output of the linear summer is the summation of these 2, that is minus the sin omega Ct minus cos omega Ct. So which can be written as minus of sin omega Ct plus cos omega Ct. Okay, so for simplification, let us multiply this expression with 2 root 2 and divide it with 1 by root 2, so that we can write this equation as minus root 2 into 1 by root 2 sin omega Ct plus 1 by root 2 cos omega Ct. So this 1 by root 2 can be written as cos 45, and this 1 by root 2 can be written as sin 45. So this is in the form of cos A sin B plus sin A cos B, so that we can write this one as sin A plus B, that is sin omega Ct plus 45. So which is equals to minus root 2 sin omega Ct plus 45. And sin theta can be written as sin 180 minus theta. Sin theta can be written as sin 180 minus theta. Therefore, this expression can be written as sin 180 minus omega Ct plus 45. So which is 135 minus omega Ct, minus root 2 sin 135 minus omega Ct. So which can be written as root 2 sin omega Ct minus 135. Since sin minus theta is equals to minus sin theta, therefore multiply the internal term with minus 1, so that it becomes omega Ct minus 135, so that it becomes root 2 sin omega Ct minus 135. Therefore, the QPSK output phase for the transmission of 00 is minus 135 degrees. For the transmission of QPSK output phase for transmission of 00, it is minus 135 degrees. Similarly, so we can even generate the phase for all the debits 0, 1, 1, 0, 1, 1. For 0, 1, the output is root 2 sin omega Ct minus 45. For Q is equals to 1, I is equals to 0, the output is root 2 sin omega Ct plus 135. For Q is equals to 1, I is equals to 1, the output is root 2 sin omega Ct plus 45. So these are the different phases. These are the different phases. So for 0, 0 minus 135 degrees. 0, 1 minus 45, 1, 0 plus 135, 1, 1 plus 45. So this figure shows the truth table of the phases. And this figure shows the phasor notation. So in the first quadrant, we'll be having 1, 1. Okay. So 1, 1 is in the first quadrant, root 2 sin omega Ct plus 45. So this indicates root 2 sin omega Ct plus 45, and this indicates 1, 0, 1, 0. So which is 1, 0 means root 2 sin omega Ct plus 135, and 0, 0. This is 0, 0. So which is root 2 sin omega ct minus 135, and here it is root 2 sin omega ct minus 45. So this is the phasor notation. And the constellation diagram for QPSK. So as we have already discussed, constellation diagram is a graphical representation of complex envelope of each possible symbol state. So here 4 possible symbol states are there. 4 possible symbol states are there. So one symbol state is at an angle of plus 45, and another one is with the plus 135, and another symbol is with minus 45, and another one is with minus 135. So the 4 symbols are represented on the axis, x-axis and y-axis. So here x-axis represents the in-phase component and y-axis represents the quadrature phase component. So the 4 symbols fall on the circumference of this circle at equal distance. If you see that, so we can see that with QPSK, each of the 4 possible output phasors has exactly the same amplitude, root 2. Therefore, the binary information must be encoded entirely in the phase of the output signal. Entirely in the phase of the output signal. So these are the carrier phases: pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. Okay. And this is another way of representation of constellation diagram of QPSK. So this is another constellation diagram. So where the phases are 0, pi by 2, pi and 3 by 2. So we can represent in the phasor constellation diagram can be represented in different ways. So in this case, the phases are 0, pi by 2, pi and 3 by 2. So each one with a phase difference of 90 degrees. Here also, each one is with a phase difference of 90 degrees. Since there were 4 different phases. Okay. So this is the way how we can represent the signals. So this signal indicates the I channel bits, and this one represents the Q channel bits. But in QPSK, we will transmit the signals as bits, means a group of 2 bits. 1 1 0 0 0 1 1 0, so which are represented by means of these signals with different phases. So see here, suppose if you want to transmit 10 01 1100, so 10 means 10 is phase shifted by means of plus 135 degrees, plus 135 degrees. So here it starts from here and ends at this point. Okay, and next 01, so 01 is with minus 45 degrees. Minus 45 degrees means, so here it starts with minus 45 degrees. So here this indicates the phase change in each of the bit group, each of 2-bit group. Okay, so in the similar fashion, 1 is represented by means of plus 45 degrees phase shift, and 0 0 is represented by means of minus 135 degrees. That means these 8 bits are transmitted by means of 4 symbols, 4 signals, 4 signal states in the case in the QPSK system, the QPSK system. So this is another way to represent. So here the constellation diagram 1. So with these phases, plus 45 minus 45 plus 135 minus 135, we have represented each 2-bit group. Here we have represented it in another way, since we can also represent the phases as 0, pi by 2, 3 pi by 2 and 5 pi by 2. Okay, so 0, pi by 2, pi and 3 pi by 2. So here we can represent 0 0 as with the 0 phase, 0 1 with 90 degrees phase, 1 0 with phase of pi, 1 0 with phase of pi. Okay, 1 0 with phase of pi, and 1 1 is with the phase of 3 pi by 2. So in this way we can transmit the signals. Coming to the bandwidth considerations of QPSK, with QPSK, because the input data are divided into 2 channels, the bitrate in either the I channel or the Q channel is equal to 1/2 of the input data rate, which is equals to FB by 2. And since bandwidth is equals to baud rate and baud rate is equals to bit rate by n, since here we are transmitting 2 bits to represent one symbol state, therefore bit rate by 2, which is equals to RB by 2. Okay, so this is the bandwidth considerations of QPSK. Now coming to the QPSK demodulator. So this figure shows the QPSK demodulator. So it comprises with a power splitter and product detectors and QI combiner. It's a bit combiner. Okay. So initially the power splitter directs the input QPSK signal into I and Q product detectors. Since here the input to this power splitter may be either of the 4 phases, minus sin omega Ct, minus cos omega Ct, minus sin omega Ct plus cos omega Ct, or plus sin omega Ct plus cos omega Ct, and plus sin omega Ct minus cos omega Ct. So at the input of this power splitter, we may have either of these 4 phases. So this power splitter directs this input QPSK signal to the I and Q product detectors and carrier recovery circuit. So here the carrier recovery circuit reproduces the original transmitted carrier oscillator signal. So it has to recover the original signal, right? That means the recovered carrier must be frequency and phase coherent with the transmit reference carrier. And the QPSK signal is demodulated in the I and Q product detectors, which generate a original I and Q data bits. It generates original Q and I data bits. So the output of these product detectors are fed to the bit combining circuit, where they are converted from parallel I and Q data channels to single binary output data stream. So when these are sent to the bit combiner, so it combines these 2 I channel and Q channel bits and the data channels to a single binary output data stream, and parallelly it sends as single binary output data stream. Okay, so let us consider one example here. As we know that the incoming QPSK signal having 4 possible output phases. Let the incoming QPSK signal be minus sin omega Ct plus cos omega Ct. Okay, so let us consider this case, minus sin omega Ct plus cos omega Ct. So this is the one of the inputs to the I product detector, and other input is the recovered carrier sin omega Ct. So for this I product detector, minus sin omega Ct plus cos omega Ct is one input and sin omega Ct is another input. Okay, so therefore at the output of this product detector of I channel, we will be having minus sin omega Ct plus cos omega Ct multiplied by sin omega Ct. Okay, so for the I channel, minus sin omega Ct plus cos omega Ct multiplied by sin omega Ct. Now this is the QPSK input signal and this is the carrier. Therefore, minus sin omega Ct into minus sin omega Ct plus cos omega Ct into sin omega Ct, which is equals to minus sin square omega Ct plus cos omega Ct into sin omega Ct. And we can write this sin square omega Ct as 1 minus cos 2 omega Ct by 2. So you should be thorough with all the trigonometric expressions to solve these equations. So sin square omega Ct can be written as 1 minus cos 2 omega Ct by 2 plus this is in the form of cos into sin, cos A sin B. So 2 cos A sin B can be written as sin A plus B plus sin A minus B. Since here the multiplier 2 was not there, therefore multiply it with 2 and divide it with 2 so that we can have 1 by 2 sin A plus B, that is sin omega C plus omega C into t plus half sin omega C minus omega C into t. So that at the I channel product modulator, the output of the I channel product modulator is minus 1 by 2 plus 1 by 2 cos 2 omega Ct plus 1 by 2 sin 2 omega Ct plus 1 by 2 sin 0. So this becomes 0, and these two terms are double frequency components, and these double frequency components will be suppressed when they are passed through the low pass filter. When they are passed through the low pass filter, the double frequency components will be suppressed. So at the bit combiner, we will be having minus 1 by 2 volts. Minus 1 by 2 volts. So this minus 1 by 2 volts is represented as logic 0. This is represented as logic 0. Therefore, I is represented as logic 0. So in the similar fashion, for the Q channel, we have to do the same procedure. The product detector inputs are cos omega Ct and minus sin omega Ct plus cos omega Ct. Therefore, at the Q channel, minus sin omega Ct plus cos omega Ct multiplied by cos omega Ct. So this is the QPSK input signal and this is the carrier. And we have to multiply these two things so that we will be getting Q is equals to 1 by 2 plus 1 by 2 cos 2 omega Ct minus 1 by 2 sin 2 omega Ct minus 1 by 2 sin 0. And these double frequency components are again suppressed by means of low pass filter, so that at the output of Q product modulator we will be getting 1 by 2 volts. So which is represented as logic 1, which is demodulated as logic 1. Therefore, the I channel product modulator output is logic 0 and Q channel product modulator output is logic 1. Therefore, the demodulated I and Q bits 0, 1, 0, 1, which corresponds to the constellation diagram. Okay, so that corresponds to the constellation diagram. So it is I is 0 and Q is 1. I is 0 and Q is 1. I is 0, Q 1 means here it is placed here. I is 0, Q is 1. This one. Minus sin omega Ct plus cos omega Ct. So this shows the point on the constellation diagram of the given input data. So this is regarding the QPSK modulation and demodulation. QPSK modulation and demodulation process. Now another important modulator is 8PSK modulator. So this is the 8PSK modulator. So in 8PSK, 3 bits are transmitted in a single modulation symbol. So in QPSK, we have transmitted 2 bits in a single modulation symbol. Whereas in 8PSK modulator, 3 bits are transmitted. So 3 bits means there exists 8 number of levels. 8 number of levels means these 3 bits are represented as 8 possible conditions as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. So each of these condition is represented by means of one phase, and the phase difference is here pi by 4. Whereas in QPSK, the phase difference between the successive symbols or states is given by pi by 2. Whereas in 8PSK it is pi by 4. So that there exist 8 possible phases. And this figure shows the 8PSK modulator. This is the 8PSK modulator. So here I and Q bits are there. Along with these I and Q bits, we have another bit C. So therefore these 3 bits can be arranged into 8 possible combinations. So the I and Q bits determines the polarity of the output analog signal. So the polarity of the output analog signal. That means logic 1 is represented by plus 1 volt and logic 0 is represented by minus 1 volt. Whereas this C bit, C or C complement. So this bit determines the magnitude. magnitude of the analog signal. That means the logic 1 is represented by 1.307, logic 1 is represented by 1.307 and logic 0 is represented by 0.541. 0.541. So these are the relative values. These two are the relative values. Okay. So consequently, with two magnitudes and two polarities. Okay, two magnitudes and two polarities, 4 different output conditions are possible at each of the I and Q channels. So here we will be having 4 different conditions with Q channel plus 1 minus 1 with C dash 1.307, 0.541. So 4 conditions exist at each I and Q channels. So here 4 conditions, here 4 conditions. So that we will be having total 8 possible conditions appear. 8 possible conditions appear. Okay. So from this one, the 2 to 4 level combiner converts it into a signal, and this signal will be multiplied by means of carrier frequency in the product modulator, and the linear summer sums up the outputs of both the product modulators from I channel and Q channel. Okay, so for example, let us consider the I is equals to 0, Q is equals to 0, C is equals to 0 condition. I, Q, C is equals to 0, 0, 0 condition. Okay, so here the I and Q indicates the polarities, C indicates the magnitude. Suppose if I is 0, 0, I is 0, C is 0. I0 means it is represented by -1 volt. C0 means logic 0 for C is 0.541. Okay, so C is 0.541 at logic 0 and C is equals to 1.307 at logic 1. So since I is equals to 0, C is equals to 0, I is -1 volt, C is 0.541, which is regarded as -0.541 volt. The output is regarded as -0.541 volt because at the input of this 2 to 4 level converter, so we have 4 combinations with respect to this I channel and the C beta. Therefore, when I is equals to 0, C is equals to 0, it is 0.541 volt. And when I is equals to 0, C is equals to 1, since for logic 1, C is equals to 1.307 and I0 means -1 volt. I10 means it is -1 volt. So, this 01 is represented as -1.307 volt. Similarly, when I is equals to 1, it is +1 volt and C is equals to 0 means logic 0 for C 0.541 volt. Therefore, plus 0.541 volt. And for 1 the output is plus 1.307 volts. So these 4 conditions exist at the input of this 2 to 4 level converter. Right? So here we have assumed that 0, 0, 0 is the condition. 0, 0, 0 means for I channel, the inputs are I0, C0, and for Q modulator, Q2 to 4 level converter, Q0, C complement means C1, Q0, C1. Okay, so therefore at the input of product modulator or at the input of this 2 to 4 level converter, this is 0, this is 0, 0, 0. The two inputs to this 2 to 4 level converter are -1, 0.541, -1 plus 0.541. So the product is -0.541 exists at the output of this 2 to 4 level converter. So which becomes input to one of the inputs to the product modulator. And another input to this product modulator is carrier sin omega ct. Therefore, For I product modulator, the two inputs are minus 0.541 sine omega Ct. Minus 0.541 and sine omega Ct. Therefore, the output of the I product modulator is given by minus 0.541 sine omega Ct. Okay. Similarly, the two inputs to the Q channel. So this is 0, this is 1 since C complement. So 0 means it is represented by minus 1 volt multiplied by 1.307 since C dash is equals to 1. So 1 is represented by means of a magnitude 1.307. Therefore, at the output of 2 to 4 level converter, it is minus 1.307. So which becomes input to product modulator. Therefore, the two inputs to product modulator are minus 1.307 and cos omega Ct. Minus 1.307 and cos omega Ct. So therefore, the linear sum or output is I channel output and Q channel output. Therefore, minus 0.541 sin omega Ct minus 1.307 cos omega Ct. So after simplification, we will be getting 1.41 sin omega Ct minus 112.5 degree. Okay, so after simplification of this one, we will be getting 1.41 sin omega Ct minus 112.5 degrees. Therefore, for binary 0, 0, 0, the output phase for 8 PSK is minus 112.5. Minus 112.5 degrees. So the amplitude here is 1.41. Similarly, for the remaining tri-bit codes, the procedure is same. The procedure is same. So we have 8 combinations for 0, 0, 0. So just now we have derived, and minus 112.5 degree is the 8 PSK output phase for 0, 0, 0. And the procedure is same for the remaining 7 conditions. For 0, 0, 1, it is minus 157.5 degree. For 0, 1, 0, minus 67.5 degree. For 0, 1, 1, minus 22.5 degree. For 1, 0, 0, plus 112.5 degree. For 1, 0, 1, plus 157.5 degree. For 1, 1, 0, plus 67.5 degree, and plus for 1, 1, 1, plus 22.5 degree. So these are the 8 different phases to represent each of the signal conditions. And this figure shows the phasor diagram. So how all these tri-bits are represented on the phasor notation by means of phasor notation. Okay, and this figure illustrates the constellation diagram of 8 PSK. So 0, 0, 0 is with minus 112.5. So here it is there. 0, 0, 0 is minus 112.5 degree. Okay, so that means here the different phases we are having. So just now we have seen the different phases, and all these phases are represented on the constellation diagram. Okay, and this is another way to represent the 8 PSK by using constellation diagram, where the phase difference between all these are 45 degrees. 45 degrees. So for the symbol for one symbol it is 0 degree. For another symbol it is pi by 4, and another symbol is represented by means of pi by 2 and 3 pi by 2, pi, 5 pi by 4, 3 pi by 2, and 7 pi by 4. So these are the phases for this particular notation, and the phases for this constellation diagram is different. Okay, and this is the way to represent the transmission of 3-bit group. So suppose if there were these 24 bits are represented by means of 8 3-bit codes, and each tri-bit code is represented by means of its equivalent phasor symbol. Okay, so 0, 0, 0 is represented by means of a sinusoidal wave of minus 112.5 degree, and 0, 0, 1 is represented by means of minus 157.5 degree, and 0, 1, 0 is represented by means of minus 67.5 degree, and so on. Okay, so this is the 8 PSK modulator. So the bandwidth considerations are So with 8 PSK, because the input data are divided into 3 channels, the bitrate in either the I channel, Q channel and C channel, so is equal. Therefore, which is equals to 1/3 of the input data rate, which is given by FB by 3. And baud rate is equals to, the bandwidth can be represented by minimum bandwidth is equals to baud rate, which is equals to bit rate by n. So here we are transmitting 3 bits per each symbol. Therefore, the baud rate is equals to RB by 3. In the QPSK, the baud rate is equals to RB by 2. In 8 PSK, it is RB by 3. Okay. So in this case also, each position is of equal magnitude. So all are with different phases. All are with different phases, but with equal magnitude. So the magnitude is 1.41, which is constant. Okay, so the tri-bit condition is contained only in the phase of the signal, not in the amplitude of the signal. Okay, so since the magnitude is same for all 8 tri-bit conditions, therefore for the 8 PSK condition is contained only in the phase of the signal. So here we have considered two PAM levels, 1.307 and 0.541. Their relative values, and any levels may be used as long as their ratio, that is 0.541 by 1.307, and their arctangent is equals to 22.5 degree. Okay, so if their values were doubled, means 1.307 is doubled, which is 2.614, and if 0.541 is 1.082. So the resulting phase angles would not change in this case also. So the levels has to be maintained. The relative levels has to be maintained. So the resulting phase angles would be same, even if we have doubled the magnitude values. Only the magnitude of the phasor would increase proportionally. The magnitude will increase proportionally. And this figure shows the 8 PSK demodulator. This figure shows the 8 PSK receiver. So it contains a power splitter and a product detectors and 4 to 2 level A to D converters here and bit combiners, bit splitters. Okay, so here the power splitter directs the input 8 PSK signal to the I channel and Q channel, that is I product detector and the Q product detectors. And here the carrier recovery circuit also. So we can also transmit this signal to the carrier recovery circuit. So the carrier recovery circuit reproduces the original reference oscillator signal. Okay, so the incoming 8 PSK signal is mixed with the recovered carrier in the I channel detector and with a quadrature carrier in the Q product detector. And the outputs of these product detectors are given as inputs to the, so these are 4-level PAM signals. The outputs are 4-level PAM signals which are given to 4-level to 2-level A to D converters. 4-level to 2-level converters. Okay, so the outputs from this I channel 4 to 2 level converter are IMC, in channel bit and C bit, magnitude bit. Whereas the outputs from the Q channel 4 to 2 level converter are Q and C bar. This Q and C bar bits. Therefore, the parallel to serial converter is there. So this is a parallel to serial logic circuit converter. So which takes the IC from this I channel analog to digital converter, QC bar from 4 level to 2 level converter from the Q channel. Okay. So these bit pairs to serial IQC. So these are converted into serial IQC output data streams. So this is the 8 PSK receiver. This is the 8 PSK receiver. Coming to the comparisons, to the on-off keying, which is the binary amplitude shift keying, the minimum bandwidth is R. For BPSK also, the minimum bandwidth is R. For FSK, the minimum bandwidth is 2 into delta F plus R. 2 multiplied by delta F plus R. That is 2 delta F plus 2R. Whereas in DPSK, the minimum bandwidth is 2R. And QPSK, the minimum bandwidth is R by 2, since 2 bits are transmitted per symbol. And in 8PSK, the minimum bandwidth is R by 3, since we are transmitting 3 bits per symbol. Okay. So these are the very important concepts of DPSK, DEPSK, QPSK and 8PSK. And now, before going to these objective type questions, take 5 minutes break, refresh yourself and come in 5 minutes. And afterwards, we'll discuss about these objective type questions. Welcome back, my dear students. Now let us discuss about some of the objective type questions and gate oriented problems. First one, in differential PSK, the data is. So in differential PSK, the data is encoded differentially, decoded differentially, encoded and decoded differentially, none of them mentioned. So encoded differentially is the correct answer. So before using PSK, a signal will be encoded differentially. A differential code by means of differential code. That means the difference between the two bits are going to be encoded. Therefore, option A, encoded differentially, is correct option. In DPSK technique, the technique used to encode the bits is AMI. AMI means alternate mark inversion, differential code, unipolar written Z format, Manchester format. So we are not using AMI, unipolar, RZ or Manchester format. So we have used the differential code because the binary input information is contained in the difference between two successive signal elements rather than absolute phase. Therefore, differential code. This technique is used to encode bits is differential code. In binary data transmission, DPSK is preferred to PSK because a coherent carrier is not required to be generated at the receiver, and for a given energy per bit, the probability of error is less. The 180 degrees phase shifts of the carrier are unimportant. More protection is provided against impulse response noise. So DPSK is because it is a non-coherent form of PSK. Non-coherent form of PSK. Therefore, a coherent carrier is not required to be generated at the receiver. Therefore, its complexity is reduced and cost is also reduced. Therefore, a coherent carrier is not required to be generated at the receiver is the correct answer. Option A is correct. QPSK is a modulation scheme where each symbol consists of. So QPSK is used to transmit 2 bits per symbol element. Okay, so therefore 2 bits is the correct answer. Option B is correct. QPSK system uses a phase shift of. So in the QPSK, there were 4 possible conditions 0, 0, 0, 1, 1, 0, 1, 1, and each condition is represented by means of one phase. Different phases, 4 different phases. Okay, so the difference between the symbols with respect to their phases is equals to pi by 2. So 4 symbols each with a phase shift of pi by 2. Therefore option B is correct. Instead of a single bit, a QPSK symbol contains a byte, 4 bits, a debit, a qubit. So QPSK symbol contains 2 bits. 2 bits is known as debit. So option C, a debit, is correct answer. So debit means 2 bits. The data rate of QPSK is that of BPSK. So the data rate of QPSK is twice that of the BPSK. Since in BPSK, 1 bit is transmitted per symbol, whereas in QPSK, we have transmitted 2 bits per symbol. Therefore, the data rate is equals to, the data rate is twice that of the BPSK. 8PSK system uses a phase shift of. So in 8PSK system, there are 8 possible conditions. Each condition is represented by means of 3 bits. Okay, so that means each symbol state is transmitted by means of 3 bits with a different phase. Therefore, 8 phases will be exist in 8PSK system. And we have seen what are all the phases. Okay, and there were The difference between those phases are pi by 4. Pi by 4. Since there were 8 possible conditions with 8 different phase shifts, and they uses a phase shift of pi by 4. The bit stream 01001 is differentially encoded using delay and exclusive OR scheme for DPSK transmission. Assuming the reference bit as 1. Assuming the reference bit as a 1 and assigning phases of 0 and pi for 1s and 0s respectively in the encoded sequence. The transmitted phase sequence becomes. So this is actually the given figure. So this is a differentially encoded modulator. So the given information is 01001 and it was given that the reference bit as 1. So the reference bit is 1 here. And the exclusive OR operation. So 0, 1 is 1 and this bit becomes the previous bit for current data input, and therefore 1 exclusive OR 1 is 0 and this becomes B of t minus TB for 0, that is next bit. Therefore 0 exclusive OR 0 is 0 and now this becomes B of t minus TB for next bit 0. Therefore 0 exclusive OR 0 is equals to 0 and 0 exclusive OR 1 is equals to 1. And it was also mentioned that the phases of 0 and pi, 1 bit as 1 and assigning phases of 0 and pi for 1s and 0s respectively. So the phases are regarded as 0 and pi. So for 1 the phase is 0. For 1 the phase is 0 and for 0 pi the phase is 0. So the phases are 0 and pi for 1s and 0s. Therefore 1 is represented by means of a phase 0 and 0 is represented by means of a phase pi. So 1 with 0, 0 with pi and 0 with pi and 0 with pi and 1 with 0. So this is the encoded phase. Okay, therefore the transmitted phase sequence becomes 0, pi, 0. So option C is correct. Given a QPSK system with the following parameters, C is equals to 1 picowatt, FB is equals to 60 kbps, N is equals to 1.2 into 10 power minus 14 watts and B is equals to 120 hertz. The value of energy per bit is, so the energy per bit means EB. So EB can be calculated as power into TS or power by TS. Power by Fs. Therefore, the energy per bit is equals to 10 log C by FB. C by FB, which is equals to 10 log C is given by 1 picowatt, which is equals to 10 to the power of minus 12 divided by the bit rate, which is equals to 60 kbps, 60 into 10 cube, which is equals to minus 167.8. Next one, for the QPSK system given in the above question, the carrier to noise power in decibel is carrier to noise power. So carrier power is given by 10 to the power of minus 12 and noise power is given by 1.2 into 10 to the power of minus 14. Therefore, carrier to noise power in decibels is 10 log 10 to the power of minus 12 by 1.2 into 10 to the power of minus 14, which is equals to 19.2 decibels. In QPSK, the binary information encoded by magnitude of each phasor is magnitude of each phasor, phase of the each phasor, frequency of each phasor, and none of the above. So in QPSK, the binary information encoded by phase of the output signal. Phase of the output signal. Because the magnitude of each phasor is same. The magnitude of each phasor is same. Hence, in QPSK, the binary information encoded by phase of the output signal. Next one. For an 8 PSK signal having a bandwidth of 5 kHz, the baud rate and the bit rate respectively. So the baud rate is equals to bandwidth. Therefore, the baud rate is equals to 5000 bauds. Since the bandwidth is 5 kHz, therefore the baud rate is 5000 bauds. Okay, and the bit rate. So the bit rate is 3 times the baud rate, because baud rate is equals to bit rate by n. Therefore, bit rate is equals to 3 times baud rate. Since it is 8 PSK, number of bits are equals to 3. Therefore, bit rate is equals to 3 into 5000, which is equals to 15,000 bits per second. So, baud rate is 5000, bit rate is 15,000 bps. Option B is correct. A constellation diagram consists of equally spaced points on a circle 45 degrees apart. If the bit rate is 6000 bps, the baud rate is. So the constellation indicates 8 PSK. Since it is equally spaced points on a circle with 45 degrees apart. So 45 degrees apart means there will be 8 different points on the constellation diagram. So which indicates that it is a 8 PSK with the points 45 degrees apart. As 2 to the power of 3 is equals to 8. So 3 bits are transmitted with each signal unit. Therefore, the baud rate is equals to bit rate by number of bits to be transmitted in each symbol. So the number of bits transmitted are 3. Therefore, the baud rate is 6000 by 3, which is equals to 2000 bauds. Therefore, option D is correct. Next question. For the signal constellation shown in the following figure, the type of modulation is. So this is the constellation diagram given, and if you see, there exists 4 different points on the constellation space. Therefore, 4 points means each is spaced with pi by 2. Each is spaced with pi by 2. Therefore, 4 different symbols are represented by means of 4 states, by means of 4 different points on the constellation diagram. Therefore, it is a QPSK system. The type of modulation is QPSK, quadrature phase shift keying, which is having 4 points on the constellation diagram. Therefore, option B is correct. Next question is, the baud rate for a signal having bit rate of 1 Mbps being transmitted through QPSK using non-return to zero line coding digital encoding technique is dash signal elements per second. So here it is QPSK. So number of signal elements per second means we need to calculate the baud rate. So the baud rate is equals to bit rate by n, where n is equals to 2. Since in QPSK there were 2 number of bits, so each symbol state is transmitted by means of 2 bits. Therefore, baud rate is equals to bit rate by 2, where bit rate is given by 1 Mbps. So 1 into 10 power 6 by 2, which is equals to 5 into 10 to the power of 5 signal elements per second, or 0.5 into 10 to the power of 6 signal elements per second, or 5 mega baud. 5 mega baud. Next question is, an analog signal carries 4 bits in each signal unit. If 1000 signal units are sent per second, find the baud rate in bauds. So 1000 signal units are sent per second. So number of signal units per second or number of signal elements per second indicates the baud rate. Therefore, baud rate is equals to 1000 bauds. For the data given in the above question, find the bit rate in BPS. Since baud rate is equals to bit rate by n, and in the 17th question, it was given that there were 4 bits. The analog signal carries 4 bits in each signal. Therefore, n is equals to 4. Hence, baud rate is equals to bit rate by 4. And hence, bit rate is equals to 4 times baud rate. Therefore, 4 into 1000, 4000 BPS. The data rate of 8 PSK is dash of BPSK. So since 3 bits are transmitted per each symbol, the data rate of 8 PSK is 3 times that of BPSK, where in BPSK only 1 bit is transmitted per symbol. Therefore, option A is correct. Label the modulation schemes. So 4 different graphs are given here. So if you see the first one, it shows that it is an amplitude shift keying, because there were 2 amplitudes here. One is transmission of carrier, another one is turning off the carrier. So this is amplitude shift keying. And if you observe the second graph, so it shows 2 different frequencies. Therefore, this is frequency shift keying. And in the third graph, if you observe, so there exists 2 different phases. See here. This is one phase and this is another phase. This is one phase and this is another phase. So only 2 phases are existing. Therefore, this graph is PSK. And now the fourth one. If you see the fourth one, we will find 4 different phases. See. So this is one phase. So this is another phase. This is another phase and this is another phase. Therefore, 4 different phases we can observe from this graph. Therefore, the modulation schemes are ASK, FSK, PSK and QPSK. Therefore, option A is correct option. In 8 PSK, the magnitude of each phasor is. So in 8 PSK, the magnitude of each phasor is same. Okay. So the tri-bit condition is contained only in the phase of the signal, not in the magnitude. Okay. So therefore, option A is correct. The bit rate of 8 PSK is. Since we are transmitting 3 bits per symbol, the bit rate is RB by 3. Okay. Now, the following figure shows an 8 PSK transmitter. Given that the input to the transmitter is Q is equals to 1, I is equals to 0, C is equals to 1. The output amplitude and phase of the transmitter are respectively. So here 8 PSK transmitter is given, and it was given that Q is equals to 1, I is equals to 0, C is equals to 1. So Q1, then C bar is equals to 0. Therefore, at the input of 2 to 4 level converter of a Q channel is 1 and 0. 1 and 0. So this 1 represents plus 1 volt and C bar 0 represents 0.541 volt. 0.541 volt. Therefore, the output of 2 to 4 level converter of Q channel is plus 0.541. This is plus 0.541 and for the product modulator, this plus 0.541 cos omega Ct are the inputs. Therefore, output of Q product modulator is plus 0.541 cos omega Ct. Okay. Now, in the I channel, I is equals to 0, C is equals to 1. C is equals to 1 means its magnitude is 1.307. And I is equals to 0 means its logic level is minus 1. Therefore, the inputs to this 2 to 4 level converter is minus 1.307. Minus 1.307. Therefore, at the input of product modulator, we will be having minus 1.307. And another input is carrier frequency sin omega Ct. Therefore, the output of the product modulator is minus 1.307 into sin omega Ct. Okay, so here plus 0.541 cos omega Ct and here minus 1.307 sin omega Ct. Now the linear summer combines these two so that we will have 0.541 cos omega Ct minus 1.307 sin omega Ct. Minus 1.307 sin omega Ct plus 0.541 cos omega Ct. Okay. So, upon simplification of this expression, we will be getting 1.41 sin omega Ct plus 157.5 degree. 1.41 sin omega Ct plus 157. Okay, so the inputs to the I channel converter are I0 C1. Therefore, output is minus 1.307. Since I0 C1 means I0 C1 means minus 1.307. Minus 1.307 and this minus 1.307 and another input to product modulator is sin omega Ct. Therefore, the output of I channel is minus 1.307 sin omega Ct. Okay. And for the inputs of Q channel converter are Q1 C0 because C complement. C1 is given, C complement will be appeared at the input of Q channel 2 to 4 level decoder. Therefore, Q1 C0 means minus 0.541. Q1 means plus 1, C0 means 0.541. Therefore, the output of Q channel product modulator is plus 0.541 cos omega Ct. Therefore, at the output of a linear combiner, we will have minus 1.307 sin omega Ct plus 0.541 cos omega Ct. So, which can be written as 1.41 sin omega Ct plus 157.5 degrees. Therefore, the amplitude of the transmitter is 1.41 and the phase of the transmitter is 157.5. So 1.41, 157.5 degree. Okay, so therefore option C is correct. The following figure shows an 8 PSK transmitter given that the input to the transmitter is Q is equals to 1, I is equals to 1 and C is equals to 1. The output amplitude and phase of the transmitter are respectively. So this is similar to the previous question. Since at the input of I channel, I is equals to 1 and C is equals to 1. Therefore, the output of this 2 to 4 level converter is plus 1.307. plus 1.307 into sin omega Ct. So for I channel product modulator, the output is plus 1.307 sin omega Ct. And for the Q channel, since Q is equals to 1 and C is equals to 1, so here C bar, which is equals to 0.541. Therefore, plus 0.541 will be appeared at the input of product modulator as one input, and cos omega Ct is another input. Therefore, the output of the product modulator is plus 0.541 cos omega Ct. Therefore, the output of the linear summer is, so here it is 1.307 sin omega Ct and Q channel 0.541 cos omega Ct. 1.307 sin omega Ct plus 0.541 cos omega Ct. So which is given by 1.41 sin omega Ct plus 22.5 degree. So upon simplification of this equation, 1.41 sin omega Ct plus 22.5 degree. Therefore, the amplitude of the transmitter is 1.41 volt and the phase of the transmitter is 22.5 degree. Therefore, our answer is 1.41, 22.5 degree. Therefore, option D is correct. So, if you observe the previous example and the current example, the amplitude is same. The amplitude is same, 1.41. Therefore, for a EPSK system, the amplitude is same. Okay. So, the tri-bit condition completely depends on the phase of the signal. So, the condition is contained in the phase of the signal but not on the amplitude of the signal. Now, consider the octal signal point constellation in the figure shown below. The adjacent signal points in the 8 PSK are separated by a distance of A units. Then the radius R of the circle is. So here the radius is R. And the distance between the distance separated is given by A units. So this is 45 degrees and the radius is R and the distance separation between adjacent signal points is A. Okay, so by using cosine theorem, we can write A square is equals to R square plus R square minus 2R square cos 45 degrees. So use cosine theorem to solve the separation between two adjacent signal points. Okay, so A square is equals to 2R square minus 2R square cos 45 degrees. So cos 45 is 1 by root 2. Therefore, 2R square minus 2R square by root 2. Therefore, R is equals to A by root over 2 minus root 2. R is equals to A by root over 2 minus root 2. Option D is correct. For a QPSK modulator with an input data rate FB equal to 10 Mbps and a carrier frequency 70 MHz. Determine the minimum double-side Nyquist bandwidth Fn and the baud. Also compare the results with those achieved with the BPSK modulator. Since the bitrate in both I and Q channel is equal to 1/2 of the transmission bitrate and the transmission bitrate was given by 10 Mbps. Therefore, the bitrate in I channel and Q channel is equals to FB by 2, that is 5 Mbps. Okay, the bitrate in I channel and Q channel is given by FB by 2, half of the transmission bit rate, which is equals to 5 Mbps. And the highest fundamental frequency presented to either balanced modulator is. So in the previous class for BPSK, we have seen this similar type of problem for BPSK. So the fundamental frequency is given by FBQ or FBI by 2, FBQ by 2 or FBI by 2. So which is equals to 5 Mbps by 2, which is equals to 2.5 megahertz. Therefore, the highest fundamental frequency presented to either balanced modulator, that is either I balanced modulator or Q balanced modulator, is given by 2.5 megahertz. And the output waveform for each balanced modulator is given by sine 2 pi FAT into sine 2 pi FCT. So which can be written as 0.5 cos 2 pi FC minus FA into T minus 0.5 cos 2 pi FC plus FA into T. Okay, so in the last session we have discussed about the waveform of a balanced modulator for BPSK. Since QPSK is regarded as two parallel BPSK. Okay, so we're going to find the minimum Nyquist bandwidth for each of this balanced modulator. Okay, therefore the output waveform of balanced modulator is the product of sine 2 pi FAT and sine 2 pi FCT. So which can be represented as cos A minus B minus cos A plus B. Okay, so 0.5 cos 2 pi into FC minus A, FA into T minus 0.5 cos 2 pi into FC plus FA into T. So FC is given by, so FC was 70 megahertz. Carrier frequency was given by 70 megahertz and FA just now we have calculated, which is 2.5 megahertz. Therefore, this is equals to 0.5 cos 2 pi 70 minus 2.5 megahertz minus 0.5 cos 2 pi into 70 minus 2.5 megahertz into T. Okay, so that means 0.5 cos 2 pi into, this is 67.5 megahertz into T minus 0.5 cos 2 pi into 72.5 megahertz into T. Okay, cos A minus B minus cos A plus B, cos A plus B. Okay, so the minimum Nyquist bandwidth is then, upper sideband frequency minus lower sideband frequency. That is 72.5 minus 67.5 megahertz, which is equals to 5 megahertz. So this is the minimum Nyquist bandwidth. So in the case of BPSK, in the last class we have derived the minimum Nyquist bandwidth for the same problem. So which was given by 10 megahertz. So we got the Nyquist bandwidth as 10 megahertz. Since the upper sideband frequency for BPSK is 75 megahertz and lower frequency is 65 megahertz. Therefore, the difference is 10. The difference is 10, which is the minimum Nyquist bandwidth, which is given by 10 megahertz in the case of BPSK. For QPSK, the minimum Nyquist bandwidth was reduced to half, 5 megahertz. And the symbol rate equals the bandwidth. So the symbol rate or the baud rate is equals to bandwidth. So which is equals to 5 mega baud. 5 mega baud. So this is the output spectrum. So 70 megahertz is the carrier frequency and 72.5 megahertz is the upper sideband frequency and 67.5 megahertz is the lower sideband frequency. And the Nyquist bandwidth is 5 megahertz. The difference between USB and LSB. Okay, so it can be seen for the same input bit rate, the minimum bandwidth required to pass the output of QPSK modulator is equal to 1/2 of that required for BPSK modulator. Okay, also the baud rate for the QPSK modulator is 1/2 of the BPSK modulator. So even the symbol rate is equals to baud rate even for the BPSK. Therefore, the baud rate for BPSK is 10 megahertz and symbol rate for QPSK is 5 megahertz. and the minimum bandwidth for the QPSK system is. So the minimum bandwidth is RB by 2. Okay. So that is the transmission bit rate by number of bits. Okay. So which is given by 10 Mbps divided by 2, which is equals to 5 megahertz. Which is equals to 5 megahertz. So for this question, please go through the last session and verify the results for BPSK system also. For an 8PSK modulator with an input data rate FB equal to 10 Mbps and a carrier frequency of 70 MHz, determine the minimum double-sided Nyquist bandwidth Fn and the baud. Also compare the results with those achieved with BPSK and QPSK modulators. So here 8PSK was given. So the bitrate in the 8PSK for I and Q and C channels is equal to 1/3 of input transmission bitrate, 10 Mbps. Therefore, FBC, FBQ and FBI, all the three are equals to FB by 3, which is equals to 10 Mbps by 3. Since the transmission bandwidth, the transmission bitrate is one-third of the transmission bitrate for each of these channels, which is equals to 3.33 Mbps. Therefore, the fastest rate of change and highest fundamental frequency presented to either balanced modulator is. So the highest fundamental frequency is given by FB by 2. FB by 2 means for each of the balanced modulator it is 3.33. Therefore, the fundamental frequency, highest fundamental frequency is FBC by 2, which is equals to 3.33 Mbps divided by 2, which is equals to 1.667 Mbps. Okay, so this is the fundamental frequency. Now the output waveform of the balanced modulator. So again the same. So sine 2 pi Fa into T, sine 2 pi Fc into T. So which is represented as 0.5 cos 2 pi into Fc minus Fa into T minus 0.5 into cos 2 pi into Fc plus Fa into T, where Fc is 70 MHz and Fa is 1.667, the fundamental frequency, minus 0.5 cos 2 pi into 70 plus 1.667 MHz into T. So which is equals to 0.5 cos 2 pi 68.333 MHz into T minus 0.5 cos 2 pi into 71.667 MHz into T. And the minimum Nyquist bandwidth is upper sideband frequency, which is 71.667 MHz minus lower sideband frequency, which is equals to 68.333 MHz, which is equals to 3.333 MHz. Therefore, the minimum Nyquist bandwidth is 3.333 MHz. So if you compare the minimum Nyquist bandwidth with QPSK and BPSK, so in BPSK the minimum Nyquist bandwidth is 10. In QPSK the minimum Nyquist bandwidth is 5. Whereas in 8PSK the minimum Nyquist bandwidth is 3.333. Therefore, the minimum Nyquist bandwidth is reduced from BPSK to QPSK by 50% and from BPSK to 8PSK by an amount one-third. And the minimum bandwidth for the 8PSK is, FB by 3. That is the bit rate by n, where n is 3 in the case of 8 PSK. Since there were 8 number of levels, each condition is represented by means of 3 bits. Therefore, the transmission bit rate is 10 Mbps divided by 3, which is equals to 3.333 megahertz. The baud rate equals to the bandwidth. Therefore, the baud rate is equals to 3.333 megabaud. And if you see the output spectrum, so this is the upper sideband frequency, which is 71.667 megahertz, and carrier frequency is 70 megahertz, and lower sideband frequency is 68.333 megahertz. Therefore, Nyquist bandwidth is the difference between these two, which is given by 3.333 megahertz. So it can be seen that for the same input bit rate, the minimum bandwidth required to pass the output of an 8 PSK modulator is equal to 1/3 that of the BPSK modulator. 1/3 that of the BPSK modulator. Since in BPSK modulator it is 10 megahertz, and in 8 PSK modulator it is 3.333 megahertz, and it is 50% less than that required for the QPSK modulator. Since in QPSK modulator it is 5 megahertz. Okay, so for these problems, please go through the previous session once so that you can easily understand these problems. So these are the references, and today we have discussed about the different bandpass transmission techniques: DPSK, DEPSK, QPSK, and 8PSK. So in DPSK, the difference between two successive bit samples are going to be transmitted, encoded and transmitted. That is, the binary input information is contained in the difference between two successive signaling elements. In DEPSK, the modulator of DPSK, DEPSK are same, but in DEPSK, it avoids the carrier frequency component that was used in DPSK is eliminated in DEPSK. So in DPSK, errors occurs in pairs, and also single errors are also present, whereas in DEPSK, errors always occur in pairs. And in QPSK, each symbol is represented by means of 2 bits. So 2 bits or a group of 2 bits are transmitted per symbol, and hence the bandwidth is reduced. And whereas in 8PSK, so 3 bits are transmitted per each symbol. Therefore, the bandwidth is reduced by a factor of 3 in this case. So these are the different bandpass modulation schemes, and tomorrow we will discuss about the more general bandpass schemes, MLA signaling schemes. I thank all the organizers and technical committee for their support, and thank you, my dear students, for your enthusiasm in learning the subject. Thank you.